Hello and welcome back to PyMan Tutoring. Today we're going to be looking at the topic of significant figures. Always a tricky topic, but hopefully if we do plenty of examples, we'll be able to solidify your understanding of significant figures. So let's begin. Let's try to make a little flowchart to show how exactly we evaluate a number for significant figures. So the first thing we do is count the non-zero digits. Okay, that's straightforward enough. In step 2, we count the zeros between significant digits. Step 3, we ignore leading zeros. And then for step 4, we ask, is there a decimal point? And if there is, we go this way. And if there's not, we go this way. If there is a decimal point, then we'll call this step 4a, trailing zeros count as significant figures. If there's no decimal point, 4b, trailing zeros do not count. Let's now look at some examples using this flowchart to guide us through. Suppose we have the number here 0.00700. Step 1, count the non-zero digits. Well, there's only one of them, and that's the 7. Count the zeros between significant digits. Well, since we only have one significant digit, we can't be sandwiching any zeros. We ignore the leading zeros, so these 3 at the front don't count. And now, do we have a decimal point? Yes, we do. So we're going down the left-hand path. How many trailing zeros do we have? Trailing zeros means zeros after the last non-zero digit. And we have 2 of them. And so our grand total significant figures in this case is 3. And if we were to write this number in scientific notation, we would write it as 7.00 times 10 to the minus 3. Decimal place is moved 1, 2, 3 places. So we see here in the scientific notation that we do indeed have 3 pieces of precision information. It's worth noticing that the fact that we ignore leading zeros in this step, we ignore all 3 of these zeros here, is that they are simply providing scale information. They're simply causing this exponential factor to be altered. They're not adding to the precision of the number, they're adding to the scale of the number, and that's why they are not significant. Okay, let's do another. Let's suppose we have 0.052. Count the non-zero digits, and we have 2 of them. Count zeros between those digits, we don't have any. Ignore the leading zeros, there are 2 of them, we're not going to count those. Do we have a decimal point? Yes, we do. Do we have trailing zeros? No, we don't. So in this case, we have a grand total of 2 significant figures. And our scientific notation would indeed be 5.2 times 10 to the minus 2. And there's our two significant figures giving us precision. The other zeros are simply giving us scale information. So it's worth remembering what is providing scale and what is providing precision. Let's do another. Now, this is a bit of a strange one. 370 point. Now, I don't know about you, but I've never seen a number written in such a fashion. Usually when there's a decimal point, there's something after it. But we're giving this example just to emphasize the importance of the decimal point itself in determining significant figures. Let's follow the usual rules. Non-zero digits, we have a 3 and a 7, so we have 2. Zeros between those digits, we don't have any. We have no leading zeros to worry about. Do we have a decimal point? And in this case, we do. And how many trailing zeros do we have? Well, trailing zeros means zeros after the last non-zero digit. And so we have one of those. And so in this case, we have 3 significant figures. But notice, had this number been 370, 370, if you were just given the number 370 with no indication of a decimal point or not, it's actually quite an ambiguous case. This may have been measured very precisely to the last digit, or this 0 may indicate that this thing was only measured to the nearest 10 units. You really can't tell in the absence of a decimal point. And so you have to assume the worst case. Well, if we go through the same system, we would say that there are 2 non-zero digits, nothing between those digits, no leading zeros to worry about. Decimal point in this case would be no, and therefore the trailing zero doesn't count, and we're left with 2 significant figures just because that decimal point was missing. And so this, in scientific notation, would read 3.7 times 10 to the 2, whereas the original number would be written 3.70 times 10 to the 2. And there's the extra digit of precision. So the importance of a decimal point. Let's do some more to solidify all of this thinking. Okay, here's another relatively simple one. 10.0. Count the non-zero digits. We have just the 1. Zeros between digits, there are none. Leading zeros, nothing to worry about. Do we have a decimal point? Yes, we do. We're going left. Trailing zeros. Well, we have the last 2 digits in this number are 2 zeros, so we have 2 trailing zeros, and therefore we must list those as significant digits, and we end up with 3 significant figures. Let's do another. Okay, 705.001. Count the non-zero digits, 3 of them. Count the zeros between the significant digits. Well, this 0 is between a 7 and a 5, and these 2 zeros are between the 1 and the 5, so all 3 zeros are significant. Leading zeros, none. Yes, we do have a decimal point. So we're going this way. Do we have any trailing zeros? No, because the last digit in this number is actually a 1. And so I end up with 6 significant figures, and in scientific notation, 705001 times 10 to the 2. And there are my 6 sig figs. Okay, let's take another look at one of those ambiguous ones to make sure you're comfortable with those. 37,000. So again, we're not giving much information about how this number was arrived at. May have been measured to the nearest 1, to the nearest 10, to the nearest 100, or even to the nearest 1,000. So in the absence of any other information, we would say non-zero digits are 2, 0 is between digits, we don't have any. Leading zeros, we don't have any. Decimal point, we don't have one. And so the 3 trailing zeros do not count. We would say we have 2 significant figures, and we would write this as 3.7 times 10 to the 4. Now, if by some chance you had been given a decimal point on the end, everything changes. Now we have 2 non-zero digits still. We still don't have any zeros between those digits. No leading zeros to worry about. But now we're going down the yes path for a decimal place. And when we look on the right-hand side of the number, those last three zeros are the last 3 digits in the number, and therefore they are all trailing zeros. Trailing zeros in the presence of a decimal place, or decimal point, I should say, are significant. And so we have to count them. And so we end up with 5 significant figures in this case. And therefore the scientific notation would be 3.7000 times 10 to the, well, how many decimal places are we moving here? 1, 2, 3, 4, 10 to the 4. Okay, a couple more examples. I apologize if you've got this now, but it does seem to be tricky for a lot of people, myself included. So let's do a couple more. We're given the number 7,030. The number of non-zero digits is 2 of them, 7 and the 3. Zeros between significant figures, so 0 is between those 2 digits above. Well, we've got 1 of them. So the 0 between the 7 and the 3 counts as significant. Leading zeros, we don't have any to worry about. Do we have a decimal point? No, we don't. And since we don't have a decimal point, that means that this last 0 is not considered significant. It's scale information only. And we're left with 3 significant figures. And so we would write this in scientific notation as 7.03 times 10 to the 1, 2, 3. Now again, it's really an ambiguous case. That 7,030 may have been measured right down to the last digit, but we don't know that unless somebody puts a decimal point here, in which case everything changes. Now we have the same 2 non-zero digits. We still have 1 of the zeros between those digits. No leading zeros to worry about, but now we have a trailing 0 to worry about because we have a yes on the decimal point, and therefore we end up with 4 significant figures. And in that case, we'd be writing this number with the extra precision digit on the end. Okay. So I think that's probably enough examples to get you comfortable with that part of the procedure. The only other thing we have to look at is the cases of adding and subtracting, multiplying and dividing. So multiplication and division, first of all. The basic rule here is that whenever you're doing scientific work, measuring something, doing an experiment, you should not report your result with more precision than was available in the experiment. And that's where we use significant figures. So, for example, if you measured some quantity as 2.00, which, as we know, has three significant figures, has one non-zero value, and it has two trailing zeros after a decimal point, so three significant figures. And you measured some other quantity, some length times some width perhaps, to measure the area of, I don't know, some aerofoil in your experiment, and you were able to measure the other dimension just to one decimal place or two significant figures. Now, if we multiply those two numbers together, you might be tempted to write your answer as 7.00 with accuracy down to the hundredth in the decimal place. But in fact, what you've got here would be, again, three significant figures. Our least precise measurement was this 3.5 dimension, and therefore we're not allowed to quote the answer in more significant figures than our worst metric, and that's the two significant figures. So we must write this simply as 7.0, two significant figures. Let's look at another one. If you were asked for 5 times 5, this people find very strange. So how many significant figures have we got? We've got one significant figure. We've got one significant figure. So you might be tempted to write from your 5 times table that the answer is 25, but in fact you have now written down two significant figures. And this is where significant figures really start to confuse people, but if we follow the letter of the law, then we can only report this value of 25 to one significant figure. And so to write this with only one significant figure, we're only allowed to have one non-zero digit. We need a trailing zero, but we cannot put a decimal point, otherwise that would make it two significant figures. And so we're just left with one sig fig, or 3 times 10 to the 1 in scientific notation. So 5 times 5 is 30 when you're dealing with significant figures. Now clearly if we had measured those dimensions more accurately, then we would have been dealing with two significant figures in each case, and so we'd be quite justified in reporting the result of our experiment as 25, not 25.0. That would be three significant figures, so that's not allowed. So the same applies with division. You have to be careful with the final answer not exceeding the precision of the least precise value in your input. Now let's look at addition and subtraction, where we do things a little differently. Now for adding and subtracting, we don't use the significant figures, we use the decimal places as our precision. So let's say we have 1.26 and we're adding to it 2.3. Adding these up in the normal fashion, 6 and nothing, 6, 2 and 3 is 5. So that gives me 3.56. But if I were to report this as the result of an experiment where I added together these two values, this second decimal place is exceeding the precision of the second number here. This value is controlling the precision with which I can report my total. And so I must truncate my answer to one decimal place. Well, I've got a 6 here, so that means rounding up in the first decimal place, and so I should report this as 3.6 to one decimal place. So you go to the next decimal place and then you round accordingly. Let's look at another one. I've got 1.26 for one measurement, and I'm adding that to another measurement which I was able to measure. It's a much bigger measurement, so my result was less precise. Maybe I used a micrometer for this measurement, and maybe I had to use a ruler for this measurement, and so I lost decimal places in the larger number. Now add together in the normal fashion, ignoring precision for now. 103.56, but again, this second decimal place is exceeding the precision of this second number, so I can't use it, and so I must round up and report the answer as 103.6 to one decimal place. And so notice here that we are not really dealing with the significant figures. This number here, this 1.26 has 3 significant figures. The second number, we have 3 non-zero values, and we have a 0 that's trapped between the 1 and the 2, and so we have 4 significant figures. And actually, as it turns out, our answer has 4 significant figures. So we actually have more significant figures in our answer than we do in one of the input values. But for addition and subtraction, we focus our attention on the decimal places rather than the significant figures. So let's do a couple more of those just to solidify that idea. Suppose that you were only able to measure 500 meters to the nearest meter, and you needed to add to that a more precise value. Now if we do the simple addition, 653.105, you might be tempted to report this as your answer, but we know that this top value has no decimal places, one significant figure, whereas this bottom number has 3 decimal places and 4 significant figures. So what do? We must report our answer to the lowest precision input value, which is the 0 decimal place 500. So we must round this number down. 501 is officially the correct answer because this 3 is less than 5 and rounds down to 0. Last example, 300, and we want to subtract 47.475. And if we do this in the normal fashion, we would get 252.525. And now, as before, we've only got 0 decimal places available to us in the first number. And so we must report our answer with 0 decimal places. This 5 slightly above 5, so it's going to round up this number over here. And so I should report the answer as 253. So there you have it. I hope you find that flowchart in particular useful. I think it's the most logical way to go through each problem you're given to extract the significant digit information. Remember to always report your answers to the correct number of significant figures or decimal places, depending on what kind of operation you have performed. So that's it for PyMan tutoring in this session. See you next time. Please don't forget to like and subscribe. Thanks.